send this to your doctor. Okay, but when I said like send this to your doctor at the very start, I wasn't joking, because in this video I'm going to be talking about the hard science that disproves a lot of what's taught to be healthy today, and it's going to show exactly why glycolysis versus gluconeogenesis, preferably gluconeogenesis, is definitely the primary state. And I'm going to be going into biochemistry as well, a lot of detail. So there's going to be a lot of detail in this video. There's going to be a lot of science in this video. Oh yeah, and in addition, this is going to be basically a part 2 to the previous video I made. So the previous video I did make a lot of studies. I showed a lot of studies in there, so you can go check out that other video if you want. I say it's the science behind video. So in this video, I really do try to find the counter arguments behind some of these things, and I honestly can't find a counter argument because there's just too much overwhelming evidence that I see at this point. I don't see another alternative, so you'll be seeing why, specifically the science behind it. And please, by the way, try to prove me wrong in this video, because that's the whole point. It's really important in science to know where you're wrong. And if you can't question it, then it's not science. It's probably a cult, or maybe some sort of a really harsh ideology. So please question it. So without further ado, let's get into it. And just again to say, this video will be very heavily science detailed, so you are warned. So I'll introduce the topics first, but I won't go into much detail until much later on in the video. So first, we're going to be going over glycolysis and gluconeogenesis, and which one is more favored than the other, and I'll be giving points to one team or the other based on some mechanisms that we'll be going through the other topics, as well as the amount of ATP made by both glycolysis and gluconeogenesis. Afterwards, the second topic will be the structure of glucose and the structure of fatty acid. So we'll be going over the structure of both of these and how one or the other can be worse or better. And I'll also be linking this a little bit to collision theory, because I do believe that ROS, or reactive oxygen species, is the primary cause of age. Afterwards, I'll be talking about the Randle cycle and its importance in understanding why you cannot feed the cell both glucose and fat, because if you feed the cell both glucose and fat, it will lock both out and then problems happen. Next I'll be talking about the oxidation of glucose versus the oxidation of fatty acid in the mitochondria, and the different off products between the two, and why one or the other may be more energy efficient. Next, I'll be talking about cholesterol. Specifically, I'll be talking about LDL cholesterol and why LDL cholesterol is actually misunderstood in this case, very misunderstood. And we'll be going over the biggest study of all time, a randomized control trial called the Minnesota Coronary Heart Survey. And speaking of cholesterol, we'll be going into cholesterol for hormones, vitamin D, as well as bile acids. Finally, we'll be going into the nitrogen isotope studies and what humans previously preferred to eat based on those studies of collagen samples. Anyways, what exactly is glycolysis and what exactly is gluconeogenesis? Well, glycolysis is when we're turning glucose to pyruvate, so shown in the photo, as you can see. Some of the 3 most common enzymes used are kinases, aldolases, and isomerases. And the difference between glycolysis and gluconeogenesis is, one, in glycolysis, you're going basically from up to down, and in gluconeogenesis, you're going from down to up. So the main difference between glycolysis and gluconeogenesis in terms of enzyme use is in steps 1, 3, 7, and 10. Instead of kinases being used, specifically glycolysis, phosphatases are used, which is gluconeogenesis. So when you're going up, you're using phosphatases, and when you're going down, you're using kinases. Now, the whole point of this video is to explain why one state is preferred over the other, and we'll be assigning points to each category, and you'll be able to see at the very end of the video why one state or the other is more preferred. But we can't just go off of one specific set of information. We have to take lots of different information. So there are a couple other things that I'm not including in this video that will be related to the citric acid cycle. There's a lot of other processes that generate ATP, but we're specifically going to be talking about glycolysis and gluconeogenesis. So how much ATP is made by one glucose molecule, and how much ATP is made by a fatty acid? For instance, we'll just use palmitic acid in this case because it's most common, or it's very, very common fatty acid. So the amount of ATP made by one glucose molecule is 32 molecules of ATP. Well, how much molecules of ATP are made by one palmitic acid molecule? Well, one molecule of palmitic acid in this case would make 122 molecules of ATP. So that's almost a fourfold increase in terms of energy production. So already palmitic acid produces far, far more energy. Or in this case, we could just say fatty acid, because we're going to have to refer to this very often. Palmitic acid will not be the only one used. So even though fatty acid in this case produces 4 times as much ATP, it doesn't necessarily mean that you get 4 times the energy if we were to convert this in terms of calories. So shown by the calculations, you can see that it's not actually 4 times the amount of energy, it's around 3 times the amount of energy. But regardless, it's still way, way more energy. And yes, I don't necessarily believe calories are an accurate estimation of energy, and I talk about that in my insulin to glucagon ratio of a calorie isn't always a calorie. But regardless, just to show the amount of ATP produced and the amount of energy that the body can use based on the fatty acid versus glucose consumption, it is far favored in terms of fatty acid. So in this case, if we were to talk about the points for gluconeogenesis versus glycolysis, that is not 1 point for glycolysis, and that is 1 point for gluconeogenesis. So next, we're going to tackle this more so from a biochemistry, although I would say it's more of a chemistry standpoint, where we will talk about how glucose interacts chemistry-wise versus how palmitic acid, or just a fatty acid in general, interacts. And specifically, this applies to saturated fatty acids. I'll also be talking a little bit about unsaturated fatty acids, and we'll see why those are a little bit dangerous. So first, we'll look at a glucose molecule and how it's arranged. So as we can see in the photo, even though there is 3 forms of glucose, there's 2 main ones. One where it's a cyclic structure, and one where it is a basically straight line. Now, the difference between the two is one of them is a more high energy state because it takes higher energy to be in the straight line structure, and one of them in the cyclic structure. Now, the one in the straight line structure can cause problems, and that it can cause glycation, it can cause lipid peroxidation, it can cause glucose auto-oxidation, which is another bad problem. There's a lot of problems when glucose has this higher energy state, and it's because it wants to bind to something. It needs to bind to something in order to be stable. Now, glucose is always in equilibrium at this state. The only difference that usually changes the equilibrium is the temperature, which is a very, very big factor in equilibrium, or the equilibrium constant. Now, the main bond that actually makes glucose a little bit unstable is the aldehyde group, which is the C bonded to an O bonded to another O, and that's carbon 1. And the reason why that's really unstable is because the bond to the O, specifically not to the OH, but to the O, is a little bit unstable, and it could end up snapping basically and end up going from ring, which is more stable, to straight line, which is less stable. Now, in this case, we'll do the exact same thing, except we'll do it for fatty acid. In this case, again, we will use palmitic acid. So as we can see, palmitic acid looks completely different than glucose. Now, palmitic acid basically is just this giant hydrocarbon chain. There isn't really any lone pairs, so it can't go through any sort of resonance stabilization. So unlike glucose, palmitic acid only has one form. It cannot have another form. It cannot have a cyclic form or any other sort of form because it does not have a lone pair of electrons. This makes it far, far more stable than glucose. And a little bit later, I'll be talking about why reactive oxygen species are a really, really big deal, and how everything basically relates to collision theory, I think, which is a theory in kinetics chemistry. Now, remember, palmitic acid is a saturated fat, but there are unsaturated fats. And unsaturated fats are when there's a double bond. And when there's a double bond, or basically a lone pair of electrons, a more likely to be lone pair of electrons, the fat molecule becomes less stable. And what happens when the fat molecule becomes less stable? Well, it can cause problems. And that's why unsaturated fats can cause problems. So if these fatty acids are unsaturated, they are much more likely to cause reactive oxygen species. I'll be talking about how that works exactly a little bit in the future. But now we have to look at where exactly do these come from. Specifically, let's try applying what we just learned to the real world. So all this Ansel keys, forging data aside, and plenty of other shady data things, how exactly does this all work? So if we just apply what we learned right there, we will see that animal fats, in this case, are saturated fats, meaning they don't have that possible resonance structure, meaning that they're more stable. Plant fats, however, are unstable because they have that unsaturated bond, specifically the possible of resonance. We could possibly apply this to Alzheimer's as well, which is the case of Alzheimer's. So what exactly happens in Alzheimer's? Well, Alzheimer's is where glycation occurs in the brain, or some maybe lipid peroxidation, just basically damage. Now, how exactly might this occur? Well, as we can see, if we were to apply this theory of how chemistry of glucose versus palmitic acid, or just any fatty acid, we can see that if we are using glucose mainly as a fuel in our brain, there most likely is going to be a higher chance of glycation or causing reactive oxygen species. But if we use palmitic acid or any other saturated fatty acid in this case, the reactive oxygen species generated will be much less likely. And that's because there aren't those same structures. There are no resonance stabilization structures in palmitic acid versus the resonance structures in glucose. Now remember that this glucose molecule, when it comes to being in its unstable form, it needs to be in a higher energy state in order to do that. And as you might guess, the brain is kind of in a high energy state, and it uses most of the energy. And because of that, we could possibly assume that the brain would be considered a high energy state, meaning that there will most likely be a little bit more of that straight form glucose than there would that cyclic glucose. The cyclic glucose is the good glucose, or the usable glucose at the very least, and the straight glucose is the bad glucose because it can cause damage. Remember that the whole point behind this video is to try to apply all of this stuff to real life and to what we know. And because we can apply this to real life, it will make a lot more sense in the future why one is preferred over the other. Now remember, when it comes to palmitic acid does not have this problem. There is no bad form of palmitic acid, or in this case, more unstable form of palmitic acid, because there is no resonance structures. It only has that one form. So because of that, palmitic acid is always viable, or basically any saturated fatty acid is always viable. Now, I'm going to be talking a little bit also about glucose and the possible damage it can cause. It can cause 4 different kinds of damage. It can cause lipid peroxidation. It can cause auto-oxidation of glucose, so that's like a little more protein related. It can cause damage of the mitochondria. We'll be going into that later on in the video. Or it can cause damage through enzyme pathways. I will not go through that one, but maybe in a future video I'll go through that. So now we're going to be talking about reactive oxygen species, and specifically superoxides, and why exactly that can cause a problem, and resonance structures, and why resonance structures, for instance like the resonance of glucose that I showed before, can end up causing problems, and why you don't always want resonance structures, because sometimes those unstable forms are a little bit damaging. So superoxides aren't just a little bit bad, superoxides are really bad. And the reason why they're really bad is because they can cause this constant chain reaction to occur because of how free radicals work. Now, as you can see in the photo shown above, which is lipid peroxidation in this case, what happens is the free radical can end up constantly going through initiation and propagation, but it will not go through termination because it can reattack instead of going through termination. Now, as you can guess, lipid peroxidation would mean that it can attack a lipid. So this could be the surface of the cell membrane. This could be maybe something related to your brain, for instance, because your brain is made up mostly of lipids. You get the point, basically. The whole point is it can attack basically any sort of lipid structure and cause problems. Now, the thing is, it can also do this with other things. This doesn't just apply to lipids, but in this case, this is lipid peroxidation. It could happen to proteins as well. And it can cause a lot of damage and wreak havoc. By the way, thank you, John Soderholm from Korea. Specifically, that is lecture 14, if I remember correctly. So thank you for the lipid peroxidation figure. And as I talked about before, the brain uses 20% of the energy of the body total, which is the most by far. And yes, exactly, you might have guessed it. This means that it's in a higher energy state. And once again, this comes to glycation and glucose, and how glucose, if we assume that the brain is in a high energy state, then that means that glucose can be slightly more in equilibrium towards the unfavorable kind of glucose that we do not want. And that would mean causing damage. And it can cause a lot of damage. Lipid peroxidation was just one example. I might go into that I might go into more detail on reactive oxygen species and how they work in a future video. So let me know in the comments below. I read all the comments as of now anyways, because I can actually read all of them, and there aren't tens of thousands. If it gets to that point, I will have a difficult time. So if we want to increase the glucose in our brain, then we have carbohydrates. And if we want to increase the fat in our brain, or the fatty acid usage in our brain, we would have fats. Now, I'm going to be talking about why you can't mix them together, but just remember that carbohydrates can cause these problems, and fatty acids cannot cause these problems. So just from a standpoint of which is better, glycolysis or gluconeogenesis, we can assume that this would give 1 point for gluconeogenesis, and that leaves glycolysis still with 0 points, and gluconeogenesis with 2 points total. Next, we're going to be talking about the Randle cycle. Now, what exactly does the Randle cycle show? Well, the Randle cycle shows the competition between glucose and fatty acids for their oxidation in adipose tissue as well as muscle. And yes, I said muscle. So why is that so important? Now, there's two ways to look at the Randle cycle, and we're going to be showing the first one, where in this case, fatty acid is the primary source of energy. And in this case, when fatty acid is the primary source of energy, then glucose, specifically the glucose receptors, get blocked, and the cell refuses to accept glucose. Now, there is also the opposite, where instead of fatty acid being the primary source of energy, glucose is the primary source of energy. And when glucose is the primary source of energy, it will block the fatty acids from entering the body. Now, both of these can happen. And, well, why exactly is this so important? Well, let's assume that we, as humans, eat fats with carbohydrates. So, for instance, a burger might be a good example. Now, why is a burger a good example? Because it has fatty meat, or it just has meat in this case, and meat naturally comes with fat, and carbohydrates. So that might be in the form of lettuce, that might be in the form of the bun of the burger, ketchup, probably. I mean, there's many other things. Now, why is that so important? Well, the reason why it's so important is because we can't actually have both fat and glucose enter the cell. Why is that? Because when the glucose receptor is stimulated and the fat receptor is stimulated, you guessed it, they're both blocked. So what ends up happening is fatty acid and glucose end up getting blocked out of the cell. Now, what exactly is the problem with that? Why might that be a problem? Now, the reason why blocking both glucose and fat out of the cell is a problem is because you're damaging erythrocytes, so red blood cells. You're damaging endothelium, so that's basically the inner membrane of your blood vessels, as well as the lymphatic system, so the immune system. Now, if we were to look at this from the case of what we brought up before, which was glucose versus fatty acid, in that case palmitic acid is saturated fatty acid, then we might be able to see where some of this damage to the cells, erythrocytes, or the endothelium in this case, or lymphatic system, can come from when we block out the glucose and the fatty acid now. Now, as I talked about before, that excess blood glucose can definitely cause quite a bit of damage, and that's because of the reactive oxygen species that it can create. And as we talked about before, with the isomerization of glucose. Now, I talked a little bit about lipid peroxidation before, and just to help you, I'll show you the lipid peroxidation mechanism again. So the reason why this is really, really bad, specifically when it damages erythrocytes, or in this case, when you kill the red blood cell, is because when you kill the red blood cell, and the red blood cell ends up dying because of lipid peroxidation, or for some reason the red blood cell lyses in this case, and we talked a little bit about why the Randall cycle, if we stimulate both fat and glucose, can cause erythrocytes to be damaged. Then if we do stimulate both fat and glucose receptors on our cells and we cause the erythrocytes to be damaged, the erythrocytes will break and they will lyse. Now, why exactly is erythrocytes lysing bad? Well, the reason it's bad is because it causes, again, another chain reaction of even more reactive oxygen species. How exactly does that happen? Well, the way it happens is heme, in this case, as you can see below, heme can cause more reactive oxygen species. Now, heme is that porphyrin ring, so it's the ring structure with a metal in the middle. In this case, it's magnesium, and that is a problem. That's a big problem because we don't want free heme going around. And not only can heme cause reactive oxygen species, it can also damage hepatocytes. And as you can see, the second picture below is bilirubin. Bilirubin is where heme binds to the hepatocyte and causes bilirubin, and that'll cause like jaundice in your eyes or your skin. So that's where your skin becomes like yellow. No bueno. So based on what we learned from the Randall cycle, we can either choose to stimulate fat or we can choose to stimulate glucose. Now, we already talked a little bit about the structure of glucose and the structure of fat, and how exactly glucose is a little bit more damaging based on the chemical structure than saturated fatty acid. So that leaves gluconeogenesis with 3 points and glycolysis with 0 points still. And as you can see in the future, it's going to get even worse for glycolysis, and that's because when glucose is oxidized, it causes a little bit more problems once again. So we learned how reactive oxygen species cause problems, basically because they end up damaging our cells in one way or another. Well, in this case, we are going to be talking more about that, and specifically reactive oxygen species in mitochondria during oxidative phosphorylation. Now, remember the Randall cycle part because we're choosing to either stimulate fat or we're choosing to stimulate glucose. And remember how glucose is a little bit more unstable and the chemical structure of glucose. And remember that reactive oxygen species, you don't want them. They're bad. Now, this is where it gets even worse for glycolysis and using glucose as a fuel. What exactly does that look like? Well, shown by the picture up there. Electrons go through the electron transport chain, and they start in complex 1 and complex 2. And complex 1 and complex 2 donate their electrons to ubiquinone. And once they donate their electron to ubiquinone, they go to complex 3. And all the complexes are indicated by C's. So once complex 3 gets the electrons, it donates it to cytochrome C. And once cytochrome C gets the electrons, it donates it to complex 4. And complex 4 gives the electrons to oxygen. Now, this whole process is what generates ATP in the first place. Now, this entire process of oxidative phosphorylation requires a proton gradient to exist. And without a proton gradient, it cannot generate ATP because ATP synthase cannot crank it out. And I'm not going to go too much into detail behind that, but just remember that membrane potential is very, very important for generating ATP, or in this case, energy. Now, the mitochondria can oxidize fat or it can oxidize glucose. And first, I'm going to show the diagram of mitochondria oxidizing fat. So when the mitochondria oxidize fat, as you can see in the top left, the Greek letter psi specifically means membrane potential, and membrane potential is going up. So that's a good thing because we want to generate ATP because we want ATP synthase to work. We need energy. And as you can see on the inside of the mitochondria, it shows JO2 up. Now that means mitochondrial oxygen consumption going up. So that's a good thing. Now that we've seen the oxidative phosphorylation of fatty acid, we will look at what the oxidative phosphorylation of glucose looks like. Shown by a similar diagram of the oxidation of glucose, there are a little bit of differences. We'll just talk about one of the differences. You can see that as glucose goes through oxidative phosphorylation and goes through the whole process, it actually generates more reactive oxygen species. But there is an increase in membrane potential, which means it can generate ATP synthase, which is good because we do want energy. So even though it does generate more reactive oxygen species, and as we talked about before, all the damage that reactive oxygen species can cause, represented by ROS, it is important to remember that ATP can still be generated. So even though that does look like a bad thing overall for glucose, it is still good that it can generate ATP. So I would give glucose 1 point for that, and that gives gluconeogenesis though 1 point as well, because gluconeogenesis, or the oxidation of fatty acid, does not generate the same level of reactive oxygen species than the oxidation of glucose. So that would be 4 points for gluconeogenesis and 1 point for glycolysis. Now, instead of always talking about the small scale level of reactions, and remember, we did talk about how important saturated fat is because it causes less damage because of the reactive oxygen species than unsaturated fat. This next part that I will be talking about is very, very, very misunderstood in today's society, and I'm going to be correcting that because it's very frustrating to hear that over and over again. So the next thing I'm going to be talking about is LDL and why exactly it's misunderstood. And I really hear it all the time, and I hear doctors prescribing statins. Even my doctor said I need to have a statin, and the fact that this misinformation still goes about is quite shocking to me, and that the lipid heart hypothesis is still prevalent. But regardless, this is the world that we live in, and a lot of it's because of money reasons of why this information probably still goes about so rampantly, and it is not corrected. Now, the next thing we're going to be talking about is LDL. So first, we should start off with what exactly is LDL in the first place, and why is it so misunderstood? Well, what is LDL? Or actually, we should also ask, what is VLDL? Because that's also another thing talked about. Well, LDL is just low density lipoprotein. Okay, what does that mean? And what's VLDL? Well, VLDL is just very low density lipoprotein. Great. So they're lipoproteins. Well, what do these lipoproteins do? Well, LDL in this case, all it does is it carries cholesterol. And we'll be talking about why cholesterol is so unbelievably important. But what does VLDL do? Well, VLDL carries triglycerides. Now, you probably heard LDL is bad for you and you shouldn't have high LDL cholesterol. But instead of listening to what authority says, let's look at the largest randomized controlled trial with 9,057 patients, all in this randomized control trial with a lot of variables, very, very well controlled. And let's see what those results show instead. Well, what study am I talking about exactly? I'm talking about the Minnesota Coronary Heart Survey. And this study is massive because it shows the exact opposite, and it was completely unexpected. Even the researchers were not expecting this result at first. So what exactly did they do? Well, they took these 9,057 patients and they split them into two groups. both men. They were comprised of both men and women. And they said, okay, first group, we're going to cook all of their food in saturated fat. So saturated fat would mean lard and tallow, and that would mean animal fats. And the second group, they said, okay, we're going to cook all of their foods in unsaturated fats. So vegetable oils like Crisco and grapeseed canola oil, sunflower oil, safflower oil, all those oils. And afterwards, okay, well, let's see what exactly the results will be. What do you think will happen? Now remember, this was a randomized control trial, a giant randomized control trial. So this means that the results of this study are going to be very, very accurate. And this would account for genetics as well. So they did the study for 5 years. And as you can see by the Minnesota Coronary Heart Survey, we can see that lowering LDL by 30 milligrams per deciliter, just by 30 milligrams per deciliter, lower LDL actually increased death by 22%. Now that is massive. Now that is really, really massive, because if we just take a little example and we make up an example of, okay, person A has an LDL cholesterol of 300 and person B has an LDL cholesterol of 100. That would mean that person A has a less likely chance of dying by 140% than person B. A little bit over that, which is absolutely ridiculous. So person B is 140% more likely to die because they have lower LDL cholesterol. That is absolutely insane. Now, as you can guess, this study isn't necessarily so popular, and you could probably guess why as well. The doctors wouldn't be throwing out statins like crazy if this study was so popular and people really knew about it. It's really sad and messed up how the lipid heart hypothesis continues to plague our society and cause so many problems, and as well generate quite a bit of revenue for pharmaceutical companies. You can take that with what you want to know. So even though this study tells us that cholesterol is important, it doesn't necessarily tell us why cholesterol is important. Now, I'm going to be explaining that. That's exactly the next topic, as to why cholesterol is so important. And there's a lot of things that cholesterol helps. And it can help autoimmune disorders. It helps with vitamin D and bile acids, which also help with the immune system. Again, that's autoimmune disorders. It can help with low testosterone. It can help with tons and tons and tons of problems, as well as blood pressure. I mean, cholesterol is so unbelievably important. And I'll be showing a picture of cholesterol and the cholesterol hormone cascade and why it's so big. So cholesterol is a sterol, and it is the prerequisite needed in order to make tons and tons and tons of hormones, whether that be testosterone, whether that be estrogen. There's 3 different kinds of estrogen, so that's estradiol, estrone, and estriol. It also is important in DHT, which is testosterone. It's important in cholecosterone, cortisol. It's important in aldosterone. Aldosterone is important in regulating blood pressure. I mean, cholesterol is so unbelievably important because it makes all of these steroid hormones that are needed. They're mandatory. And when you don't have them, or maybe they're a little bit out of flux, you might guess what problems could happen. So now I talked about 3 different estrogens before. So I talked about estrone, estradiol, and estriol. Estradiol has been linked to lupus, and estriol has been linked to MS, or multiple sclerosis, and cortisol has been linked to rheumatoid arthritis. I mean, cholesterol is insanely important. So you can see how cholesterol, or a lack of it, can end up affecting autoimmune disorders. And by the way, 80% of women have autoimmune disorders. So a lot of really, really important things originate from the cholesterol molecule, because they're all synthesized from it, shown by the cholesterol synthesis cascade. Now remember that all these hormones are interlinked, so affecting one can also affect another hormone, and affecting that hormone will also affect like the other hormones. So they're all at play with each other, and it's really, really important that if you mess one up, you just know that you're also probably going to mess many, many more up, and it'll cause this chain reaction. And it's just really, really important to make sure that your hormones are in check, because if they're not in check, I mean, problems can happen really, really quickly. Now, instead of looking at everything from a biochemistry or a chemistry standpoint, we'll look at it from a evolutionary standpoint. And let's say did our ancestors go through glycolysis most of the time, or did they go through gluconeogenesis? Well, just based on the stable isotope studies, so that's basically where we measure nitrogen 15 to nitrogen 14 content, we can see by all the graphs shown, they were primarily carnivorous, and they were going through gluconeogenesis most of the time because of it. Now, being highly, highly carnivorous, I mean, even Neanderthals were really carnivorous, which is the subspecies before human. It's really, really amazing. So humans evolved on carnivory, and we're eating meat most of the time, as I think about 80% minimum of the diet. So the nitrogen 15 to nitrogen 14 content, the ratio of that indicates the trophic level of the animal. So you can see shown by the 15 to 14 ratio that humans definitely were highly carnivorous, as well as Neanderthals and other pre-humans evolving to be. So again, that would mean that gluconeogenesis would probably have 5 points and glycolysis would only have 1. Now, before I end this video, I want to ask, what exactly is the purpose of science in the first place? Now, I believe the purpose of science is to explain phenomena of the real world, and it's not for the phenomena of the real world to explain science, because if we make such a statement, then we can end up having a little bit of questionable things happening with studies. For instance, the lipid heart hypothesis and the forging of data, or just p-hacking itself. Now, the only way that we can actually explain phenomena of the real world with science and make sense of it, with it being truthful, is we have to have dependent and independent variables, and we have to be very rigorous when it comes to controlling variables, because if we don't, we can't actually see accurate results. We won't have any accurate results, and this is why I believe epidemiology studies are almost completely useless 99% of the time, because they do not control for variables. There are too many variables at play, and that's not even just including the variables when it comes to the participants lying. It also comes to memorization, like memorizing what they ate, and it's an absolutely horrific process. So I don't even believe the epidemiology studies to be studies at all. I just believe them to be cases of observation with many variables flying about. You can't really discern much out of it. So that's why in this video I talked so much about the biochemistry and the chemistry and what exactly is going on there, because if I believe that we have to work our way up from a basic principles level. So it's just like Elon Musk says, you work your way up from basic principles. So you start with what you definitely know to be accurate, and then you work your way up from there. So that's why I brought up the chemistry and the biochemistry, because if we don't work up our way from basic principles, it's very, very difficult to understand why exactly some of these things just happen in the real world, and we won't be able to make much sense of it. And so just to end this off, I want to say thank you for watching. If you have any comments, please leave them below. I read all of the comments. If you have any future ideas about videos that you might want to see, please leave them below. I post tons of videos. I will be posting a lot of videos when it comes to my lifestyle, and a lot of science videos as well as philosophical videos. If there's any other videos that you might want to see, please let me know. Even if it isn't out of the topics that I've mentioned, I'd love to just see the comments. I read all of the comments, like I said. So if you are interested in some of the content that I said before, please subscribe and turn on the notifications so you can see some of my videos come out. So without further ado, thank you for watching, and I'll see you in the next one. Peace.